Okay, let me talk for a moment about the position-preserving temporal skew. And the reason I'm talking about this is because I recently made a video response to Veritasium's Why No One Has Measured the Speed of Light. And I called it One-Way Speed of Light Veritasium Response Part 1. Now, this video, I kind of did it hastily, and unfortunately, I think 2,915 views on it, and I'm not sure how many people have gone on to part 2, part 3, part 4, part 5, but I think I can summarize all the parts with this position preserving temporal skew. And the difficulty is that a whole bunch of people have made comments saying something along the lines of, what if we did this? What if we did that? Couldn't we determine the one-way speed of light was the same in all directions? But I haven't been able to explain this very well, uh, but I was working on yet another explanation. And it occurred to me that I really need to make a video to kind of show this. So once again, imagine that you have space and time coming this way and this way. And we're just kind of mapping objects going through space and time. Let's say an object moving at the speed of light looks like this. It's going very, very fast. Space is large, time is small. An object moving less than the speed of light would look like that. Okay, or did I say at? Okay, so this one's going at c, this one's going less than c. Okay, and we want to know speed of light. If it comes back the other way, will it be the same? And I have kind of drawn that. Not, I haven't drawn those two slopes the same, unfortunately, but here's what I'm going to do. I'm going to show what a position-preserving temporal skew kind of looks like on a space-time diagram. Okay, so you can see on the edge of this book, I've drawn a straight line and or a horizontal line, and that's supposed to represent the space axis, and the other two lines are supposed to be the speed of light. Now, what happens when we do this temporal preserving, or this space position preserving temporal skew is we just do something like this. And you can see I have modified the speed of light going this way so that it's slower, and the speed of light this way so that it's almost pretty much instantaneous. But we've also changed that this line of clocks that were simultaneous have become, that are all marking like the t equals 0. Those are all marked t equals 0, but they have become desynchronized in this diagram. Similarly, if I move it this way, we can get the speed of light to go flat in one way and uh, slower in the other direction. But the times on the clocks, the t equals zeros, have become desynchronized. So the problem is you can't experiment your way out of this, because all of those events, that position preserving temporal skew did not change anything about those events. All of the clocks read the same things. All of the events, all of the events occurred relative to the clocks and rulers in the same place. No rulers changed, no clocks changed, no events, no readings on any events changed, no forces changed. But you're changing two things at the same time. And I put it up here, unless two fairly strange and unlikely suppositions are accepted and both by some strange coincidence happen to cancel one another exactly. The first is that the speed of light is different in the two directions, and the second that the times on the clocks are desynchronized to exactly cancel out the observation that the difference in that difference in speed. Now, those two strange and unlikely suppositions are bothly combined in what I just did, the position-preserving temporal skew. But those two suppositions in combination cancel out any possible observation of either effect under any circumstances, no matter how simple or complex. Down here under explanation 2, I give the transformation x prime equals x, which is the position preserving, and then the t prime equals negative kx plus t, which is t prime equals t would be time preserving too, but negative kx adds a skew by modifying modifying the time according to position. So if you're still trying to experiment your way out of this problem, you're still not getting it. The problem is that if our co-moving clocks are desynchronized, I should say if you've done the temporal preserving, the position preserving temporal skew, you have done both of these two effects. The co-moving clocks are desynchronized and the speed of light is asymmetrical. And those two effects combined cannot be detected. Your bullet velocity, your sound wave, your compression waves, your tension waves would have the same undetectable velocity asymmetry as the light. And so if you're not drawing your space-time diagram and then doing the position preserving temporal skew, you're probably not getting it. So I'll rewrite that explanation. If you're still trying to experiment your way out of this problem, you're still not getting it. A position-preserving temporal skew changes no observable phenomena. No readings of rulers are changed, no readings of clocks are changed. However, it does change the slope of the speed of light in the space-time diagram, and it changes the slope of the synchronized co-moving clocks away from the horizontal. But your bullet velocity, sound wave, compression wave, tension wave would all have essentially the same undetectable velocity symmetry as light. So whatever non-light information carrying method you find, they all have the same undetectable velocity asymmetry of light, and therefore could not be used to detect the presence or absence of that asymmetry.